Hi, I'm Tyler. In this video, I'm going to cover the Lua programming language in about 1 hour. I previously wrote a post called Learn Lua in 15 minutes. That post is basically a quick reference that you can use to just get started, a very shallow understanding of the language, or to refresh your memory if you already know it. The idea of this video is to take another step towards really mastering the language of Lua. I'm going to cover what I consider to be all of the core of the language, which isn't 100% of everything that you can do with Lua, but it does cover most of what you'll use day to day. Lua is currently at version 5.3, and I will cover versions 5.1, 5.2, and 5.3, which is pretty easy because they're all basically the same. I just have to highlight the small number of differences between those languages, those versions. You might care about older versions of Lua because some C apps will have an older version of Lua embedded in them, or if you're using Lua JIT, which is the just-in-time compiler, then you are going to be using version 5.1, at least at the time I'm making this video, that's true. This is the first in what I envision as being a series of Lua videos, tutorials, covering more and more advanced topics in Lua. You don't have to watch the rest. If you just want to know how to program Lua, this is the only video you need to watch. But I can imagine future videos covering the standard library or the C API. Basically the topics in this book. This is the official Lua book. So let's dive into the language. Let's get started. Okay, let's get started with the docs and how to install Lua. The official website is lua.org. If I click on documentation, I can see the official book called Programming in Lua. The third edition is the latest right now. The first edition is available online. You can read the entire thing for free. It's useful, but it covers an older version of the language. Another great resource is the reference manual. This is basically like a set of man pages for Lua. It covers the C API, the standard library, and all of the core language itself. It's not a great way to learn, but once you know the language, it is a great way to look up things you may have forgotten or technical detail that you almost know but you need to double check. If I click on the download link, I can download a gzip file. Once that's unzipped, well, these instructions here include downloading and unzipping. The highlighted instructions here will work you through downloading and building on Linux. To build on Mac OS X, you just have to replace the word Linux here with Mac OS X. Or you could use Homebrew. You could just type in brew install Lua. On Windows, you can use the Lua for Windows project at Google Code. I haven't used this myself, but it looks good, so I think it will probably work well. As far as the interpreter goes, once you've installed, you can just type Lua at the shell, and now you can type in statements directly. If you want to evaluate an expression, you can't just type an expression, at least not with Lua 5.2 and earlier. You have to put in an equal sign as the first character of the line, and then it will evaluate the expression after the equal sign. Control D escapes from the interpreter. You can use your favorite text editor to type in a Lua script, and then you can type in at the shell Lua and then the name of your script file, and it will execute it. If you know the absolute path of your Lua interpreter, then you can insert a first line, which is hashbang, followed by the path of your interpreter. Make sure that your file has execute permissions, and then you can execute that file directly. That's 3 ways to run Lua code. You can also run from embedded apps. Okay, let's talk about types. These are all 8 types in Lua. I'll mainly talk about these 6 highlighted types in this video. True and false are the Boolean types. The built-in type function returns a string indicating the type of the input. There's a single number type. You can type numbers in standard decimal notation, in scientific notation, or in hex like this. In Lua 5.2 and earlier, numbers are represented internally as 64-bit doubles by default. Lua 5.3 still has a single number type, but it can internally use either an integer or a double representation. The built-in toNumber function converts numbers and strings to numbers. Lua strings are immutable. You can use single or double quotes to specify them, and it doesn't really make any semantic difference which type of quotes you use. These literals can have the usual backslashes like new lines and tabs. Lua strings internally are arbitrary length byte sequences, so 0 bytes are allowed. You can type a backslash followed by up to 3 decimal digits to specify arbitrary bytes. And multi-line strings can be input by typing in 2 open square brackets, and they don't allow escapes within this type of string. The built-in toString function returns a reasonable string representation of any value. Tables are key value maps and Lua's only container type. I'm going to cover those later in the video. The nil value conceptually means no value. Undefined variables evaluate to nil. It's not an error. If you set a variable to nil, you undefine it and allow it to be garbage collected. You can also explicitly call collect garbage, but usually you don't have to because the garbage collector is running automatically. Functions can be assigned to variables and passed into and out of other functions. I'm going to talk more about functions later in the video. User data and threads are slightly advanced types that I won't cover in detail now. A user data object is basically a black box type that is used by library to wrap C-level structs, like a file star from C's standard I/O library. Thread is a coroutine instance. Assignments are global by default. Use local to make them local. Let's talk about operators. Lua has the usual arithmetic operators. It also adds exponentiation, so this is 3 squared times 2 plus 1. Division is always performed as a floating point operation, even if the inputs are integer values. Lua has a very clean modulo operator. It's capable of handling modulos with non-integer or even negative inputs. There's also a hash operator, which gives us the length of a string and works on tables, as we'll see later in the video. Lua has the usual conditional operators, or comparison operators. In the case of the not equal to operator, it's spelled with a tilde as the first character. When you compare two values that have different types, Lua always considers them not equal to each other. Lua also has the standard less than, greater than operators. In the case of strings, it tries to put the strings in alphabetical order using the current locale. The string concatenation operator in Lua is the double dot. Nil and false are the only falsy values in Lua, which is interesting because that means 0 is considered truthy. The Boolean operators are short-circuited, which means that as soon as Lua can determine the total value of the or the and clause, it doesn't even bother to evaluate the rest of the expressions, like that. I'll quickly mention how you can work with binary operators. Lua 5.2 has a bit32 module, which offers them as functions. Lua 5.3 actually adds these operators to the language itself. Lua supports assignments with multiple variables on the left and multiple expressions on the right. Lua performs this operation by first evaluating everything on the right, putting it on a stack, and then making the assignments to the left-hand side. This is important because it enables things like the swap operation I just performed. If there are more variables on the left than on the right, the extra variables become nil. If there are more expressions on the right-hand side, then everything is evaluated, but the extra expressions are thrown away. Tables are Lua's only container type. They're associative arrays, which are key-value dictionaries built using hash tables. I can set up an empty table by using an open and close curly bracket like this. From there, I can set values using this dot syntax. I can also perform lookups. This dot syntax treats the keys as strings and only works for identifiers, which means that the strings can only contain alphanumeric or underscore characters. I can also perform lookups on undefined keys, which returns nil without an error. However, if I try to perform a lookup on a nil as if it were a table, that will be an error. Lua also has a square bracket notation, which allows me to use arbitrary Lua expressions as keys. Here's an example of a number as a key via the variable a. Here's an example of a table as a key, And here's an example of a function as a value. I call the function like this. Lua also has a syntax to specify non-empty tables. In this case, I'm creating a table with the keys A, B, C, and D, E, F. This syntax works by treating the left-hand side as a string key. It has to be an identifier. The right-hand side of the equal sign is an arbitrary Lua expression. Here's an example with a function on the right-hand side. If you want to specify non-identifiers as keys, you can use a square bracket notation like this. If a table has consecutive number keys starting at 1, then it's called an array. Arrays aren't a new type, they're just tables with a specific key structure. In Lua syntax, I can specify an array by omitting the equal signs in a table literal. This is the first 4 prime numbers. When I use this syntax, Lua assigns keys as numbers starting at 1 and going up from there. I can use the hash operator to see the size of an array. Tables in Lua are considered equal only if they're identical. It is not enough for their contents to be the same, like this. In other words, the expressions that are being compared have to evaluate to literally the same table. We've already been using the built-in print statement. This statement takes a variable number of parameters. It calls toString on each of those parameters, joins them with tab characters, adds a new line to the end, and sends that all to standard out. Let's talk about functions and closures. A closure is a function that refers to variables declared outside of itself, but which are not globals. For this part of the video, I'm going to use a text editor to write my Lua because in practice you'll be using a text editor to write your code, and multi-line Lua doesn't work as well in the interpreter. I've declared a global function here called ABC. Syntax for functions always starts with the word function and ends with the word end. Within the interpreter, I can use the built-in doFile function to load and execute the script. That's what the doFile function does. Now I can call ABC with any 3 values that I like this. Similar to flexible assignments, Lua function calls accept a flexible number of parameters. If I call ABC with a single parameter, then the extra variables inside the function receive the nil value. If I call the function with extra values, the extra values are discarded. Return values work similarly. I can accept more or fewer values than are actually returned by the function. Now I'm going to define a function that returns 4 values. When you chain function calls together, the output of one function goes into the input of another, similarly to flexible assignment. So in this example, the extra return value 7 will be discarded. You can also create anonymous functions. The syntax is the same, except that you leave out the name of the function. Here's an example that returns an empty table. And you can create local functions. That means the function, considered as a variable, only has local scope. This is useful when you're writing a module. You want to call an internal function that isn't visible outside the scope of the module. Let's take a look at an example of a closure. I'm going to define a function called adder, which takes a number called x and returns an anonymous function which adds up a new number y and x. I'll load these into Lua. Now I can make a new variable called add1, which is the return value of adder1, and add30, which is the return value of adder30. These are different functions, and when I call them with the same input, say 12, I'll get different outputs. The important thing here is that each of these functions has its own private copy of the variable x with a different value. If closures are new to you, this is a basic example to see the general idea. The word chunk in Lua means any block of statements that are compiled as a unit. The most obvious example is a Lua file. I'll create a new file to demonstrate. Chunks are always treated as the body of a function, which has 2 consequences. First, local variables are not visible outside the chunk. Second, you can return values, which stops the execution of the chunk. In the interpreter, I'll use the built-in doFile function to execute the script I just wrote. The global x is left undefined since it was a local in the file. The global y is defined, and the return value r has been received from the function. Any code executed in the interpreter is compiled as a chunk. This means that variables declared as local aren't visible in the next chunk, like this. They are visible within the same chunk, though. Semicolon, by the way, is an optional line separator in Lua. I can also return values from an interpreter line, like this. The default action of the interpreter is to print out the return values. In Lua 5.2 and later, there's a nice built-in function called load, which accepts a string, compiles it as a Lua chunk, and returns a function you can call to execute that chunk. In Lua 5.1, which I'm using here, you want to call loadString to perform the same action. Here is an example. Notice that my code hasn't run yet. It's only been compiled so far. I can call F to run the chunk. Lua has two types of comments, single line and multi-line. To illustrate that, I'll create a new Lua file. Here is a regular Lua statement. If at any point Lua sees two hyphens, then the rest of that line is a comment. To start a multi-line comment, you need to use two hyphens followed by two open square brackets. And to show that this is in fact a multi-line comment, I'm going to put in multiple lines, and we'll see that they are not executed. And to show that this is the end and things are executed again, I'll create another statement. When I run this, we should only see strings 1 and 5 printed out because the rest are commented. There you go. Lua has several loop constructs. I'll start by looking at the while loop. In a new Lua script, we can create a loop that begins with the keyword while, followed by a conditional, the keyword do, and then an arbitrary block of statements, followed by the keyword end. This will count from 1 to 10 and print out the results. To verify that, I'll run the script. Let's talk about for loops. I'll start a new script. A simple for loop starts with the keyword for, and it includes a number range over which we'll iterate, a loop variable. Just like the while loop, you want to include the body of loop between the do and end keywords. We can also use a step parameter. In that case, we add a third parameter to the parameters being used for the for loop. And you can probably guess what these do just by looking at them. Maybe the only non-trivial thing is that both the starting and the ending numbers are included when I execute the loop. There we go. There is another type of for syntax in Lua using what's called an iterator. I'm not going to cover them in detail, but I will cover in a few minutes the pairs and iPairs functions, which are the most useful iterators that Lua comes with. Lua includes a break statement, but not a continue statement. I'll give you an example of break. We'll print the first number, and this will stop as soon as the keyword break is seen, so it'll only print the first number. Lua also has a repeat until loop, which is like a do while loop. The syntax is to begin with the keyword repeat, followed by a block of statements, keyword until, and then an ending condition. We can confirm that this prints out 1 through 5 by running the script. There you go. Lua 5.2 added the goto statement. I'm not going to cover that in detail in this video. In my experience, the vast majority of code works well with the loop constructs we've already covered, not using goto. Although I also feel that in rare cases, a goto is the best control flow mechanism to use. iPairs functions allow us to iterate over tables. I'll demonstrate by defining a table with 3 key value pairs. We can use an iterator with a special form of the for loop using the in keyword, like this. I'll print out all the key value pairs in the table. The first loop variable, which is k here, gets the keys from the table. The second, which is v here, gets the values. Tables don't store any order information about keys, and we don't get any guarantees about the order of iteration. I can also use a single loop variable if I only care about the keys. If I only care about the values, then I do need to use two loop variables, but as a convention to other programmers, I can set an underscore as the first loop variable. This indicates that I don't really care about the value stored in the underscore variable. The iPairs function works with arrays, so I'll define an array with some Fibonacci numbers in it. The syntax to use iPairs is the same as for pairs, like this. The difference is that iPairs expects its input table to be an array, and that it iterates over keys in order starting from 1. To summarize, use iPairs to iterate over an array that needs to be processed in order. Otherwise, use pairs. The if statement in Lua is straightforward. I'll start by giving a very simple example. You start with the keyword if, a condition, the keyword then, followed by any block of statements and the keyword end. It does what you would expect it to do. I'll show you a more complicated example now. You can have an else if clause, and you can have an else clause. Both of those are optional. You could have one without the other, or just have the if clause by itself. So far we know how to print to standard out using the print function. Now I'm going to talk about two functions in the standard library called io.read and io.write. io is a table. It's a table that has some functions as some of its values. It's part of the standard library, and if you're using Lua from an embedded app, such as a game, the developers may have chosen to exclude some of the modules of the standard library, or all of them, for security reasons probably. So it's not guaranteed that you have access to these functions. By default, such as in the interpreter, you do have access to these functions though. So I'm going to tell you about them since they're very useful. The default action of io.read is to read a line from standard in. The return value is a string with the line. However, it excludes the new line character at the end of the line. You can also use io.read by giving it a number parameter. This asks io.read to read up to that many characters from standard in. As you can see in this example, the variable s will have 4 characters. io.write acts very similarly to print. I'll give it a string as input here. One thing that's interesting is that the string contained a new line, and io.write did not add a new line. That's the way io.write behaves. Print, on the other hand, if I give it the same string, will add a new line. io.write also accepts multiple parameters. If it takes a number as an input, then it converts that to a string. Otherwise, it only accepts strings. It concatenates multiple parameters together without any spaces between them, and never adds a new line at the end, like that. The I/O table is an example of a module. The word module in Lua basically means library. The built-in require function is the standard way of including modules. It's sort of like an import statement in Python or a pound include in C-like languages. In order to demonstrate modules, I'll build a simple one called vec.lua. This will be a module that works with vectors, two-dimensional vectors. I'll start by defining a function that computes the norm of a vector. The norm of a vector is basically its distance from 0. I'll also define a distance function which computes the distance between any two given two-dimensional vectors. I can reuse this norm function to help me with that calculation, like this. Remember that chunks are compiled as the body of a function, so a good way to get the vec table out is to return the value. Next, I'm going to describe 3 functions building up in complexity to the require function. The simplest is the load file function, which loads a Lua file, compiles it as a chunk, and then returns a function which will execute that chunk. Load file itself does not actually run the code. If I call the function, then the code is finally run. So now I should have a table in the vec variable, and I can call functions on it. For example, here's the norm of 1, 1. The next function in complexity is the function doFile, which works very similarly to load file, except that it also takes the extra step of actually executing that code and returning the value from the chunk. So v will have the same functions as vec above. The last function that I'll describe is the require function. The first difference you'll notice is that I don't have to add the .lua file name extension at the end of require. Now this is actually a different table than the previous two values, although it has the same functionality. One difference between require and doFile is that require caches its values. So if I call it again with the same input, it will actually give me the same return value as before, as opposed to re-executing the module. The final difference is that require searches through a path specified in the package.path string. So it will look in multiple locations for your Lua files. It's a common practice to assign the return value of a require call to a variable of the same name as the module, like this. There's two categories of errors that can be communicated across function calls. The first category includes exception-like errors. The second includes errors given by return values. Now the documentation avoids words like exception, throw, and catch, but I'm going to use the exception language because I think it clearly communicates the behavior that's going on here. First, I'll show you an example of the standard library throwing an error, which is then caught by the interpreter and printed. In this case, there's a bad argument to the io.write function. If you want to throw a custom exception error, then you can call the built-in error function with a string describing the error. In this case, my function f will throw that error, the interpreter will catch it, and print my error message. The built-in assert function accepts as input a boolean and an error message. It throws the error message if the boolean is false, like this. However, if the condition is true, then it simply returns the inputs that it receives, like that. A common pattern in Lua for functions that return error messages is to first return a boolean indicating success or failure, followed by, in the success case, the useful return values, or in the failure case, an error message. Assert works well with this pattern. I'll demonstrate by creating two functions that return success or failure depending on which one I call, and we'll see that assert easily wraps these function calls. In this case, it'll throw the error message, and in this case, the good case, it will simply return the useful return values. The built-in pcall function makes protected function calls. It basically wraps a call to catch exceptions. You use it by first sending in the function that you want to call, followed by parameters that you want to give to it. It calls the function with the given parameters. The first return value is going to be a boolean indicating success or failure, and the others are either going to be the called function's return values or an error message if an exception was thrown. I'll give an example of a case where an exception is thrown. In summary, pcall converts exception-like errors into return value errors. I like to think of it as a sort of inverse of the assert function. There's another built-in function called xpcall, which offers basically the same functionality as pcall, except that one of its input parameters is a callback function to handle exception-like errors. I'm going to talk about what I think are the most useful functions in Lua's standard library. We'll start with file operations. You can open files in Lua with the io.open function like this. The first argument is the file name and then the mode, just like fopen in C. W means write mode, and you can use R for read mode. You can write to a file by using the write method, giving it the string that you want to write. I used a colon here instead of a period because the write method treats f as an object being acted upon. I'll talk more about the colon syntax later. You can close the file by using the close method. Reading a file is the same except that we use the read method. This method has the same input structure as io.read. Here's an example. There we go. Next, I'll talk about the pieces of the math module that I find most useful. You can find the square root of a number using the math.squareroot function. The math.random function behaves differently depending on the number of inputs it receives. With no inputs, it returns a pseudo-random float between 0 and 1. It can equal 0, but is always less than 1. With one input, it returns a pseudo-random integer between 1 and the input, including both endpoints as possible outputs. With two inputs, it returns a pseudo-random integer between the two inputs. Again, the endpoints are possible outputs. The math module has common trig functions which work in radians. Pi is available as math.pi. Now for some functions in the string module. The string.sub function returns the substring of its first input between two indices given as parameters. Here's an example. Both endpoints are included. In this example, C is the fourth letter and E is the seventh. You can also use string.sub as a method call with the colon syntax like this. Remember that Lua strings are arbitrary byte sequences. The string.byte function returns the numeric value of a byte within a string like this. Again, you can call it as a method call using colon syntax like this. The string.format function works like the printf function found in many other languages. Here's an example. I won't cover Lua's format specifiers in detail, but they are mostly the same as those in C. Now we'll cover metatables. Every table in Lua has an optional property called a metatable. It's completely separate from the key value data and is set to nil by default. Metatables allow us to add object-oriented behavior to tables, among other things. With metatables, we can overload operations performed on tables. Most useful operations to overload are the getting and setting of key value pairs, which is the only metatable usage I'll cover carefully in this video. We can set a table's metatable using the built-in setMetatable function, like this. The first parameter is the table whose metatable is being set. The second is the metatable itself. The first input is also the return value. Even though key A exists in the metatable, it doesn't exist in T itself. Only special keys in a metatable can change a table's behavior. I'll mention a couple of these special keys in just a second. We can get a table's metatable using the built-in getMetatable function, like this. Let's change the behavior of T by providing a backup table. If a key isn't in T, Lua will look for it in the backup. $_index as a key in a metatable is known to Lua as providing a way to handle failed key lookups. If the index value is another table, then Lua will use that other table as a backup location to find key value pairs. Keys already in T itself will overshadow any values in the backup table, like this. We'll see in a minute that this functionality enables a kind of class inheritance behavior. We can also overload a table's behavior when a key value pair is set for a new key. This works by setting a function as the value of the $_new_index key in a metatable. This function is called by Lua with the table, key, and value being set as parameters. Here's an example. We tried to set a new key in T. T's metatable has a new index function, so that function is called instead of setting the value. Our function could have saved the data somewhere, but it just printed things out. The new key string is still not a key of T. Setting values on existing keys of T does not call our new index function. This new index functionality allows us to make things like read-only tables, proxy tables, or tables that take action on every data access to them. There are two built-in functions called rawGet and rawSet, which can access a table's data while ignoring its metatable. I won't cover these functions in detail, but I wanted to let you know that they exist. Now let's talk about using tables as classes. Lua doesn't directly contain classes, but it's easy to use tables in an object-oriented way. When I talk about classes in Lua, I just mean tables used so that they combine data and behavior in one place and where inheritance is possible. When you treat a table as a class instance, you want to make sure that method calls have access to the instance. In C++, you would use the this pointer. In Python, you would use self. Lua also uses a parameter called self. I'm using the word method even though Lua itself doesn't distinguish between functions and methods. Lua sees them all as functions. So when I say the word method, what I mean is a regular Lua function that meets two conditions. The first condition is that it's a value in a table used as a class, and secondly, it expects its first input to be a self parameter when it's called. This will all become more clear with examples. Now is a good time to explain colon syntax for function definitions and function calls. The main purpose of colon syntax is to make it easier to define and call methods on tables used as classes. Here's how we can define a method using regular syntax. We can call the method like this. When you're defining a function in a table, using a colon instead of a period inserts a first input parameter called self. So G and F are essentially the same. When you call a function in a table, using the colon inserts the table as the first parameter value passed to the function. So this is the same as this. That is everything about colon syntax. Let's make some example classes. I'll make two classes. The first is a class that can print out values from a sequence of numbers that increase by 2 with each step. After that, we'll make a subclass based on the sequence of square numbers. First, I'll type out a constructor, and then I'll use it, and then I'll explain what each line does. We can use this to get a new sequence instance like this. The first constructor line creates a new table that will be the returned instance. The second line makes sure that sequence itself has an index key pointing to itself. The purpose of this is to make sequence useful as a metatable, where instances will find their methods. The last line sets sequence as the metatable for the new instance and returns the new instance. So now we have a constructor and an instance, but we can't actually do anything yet with the instance. Let's change that by defining a couple methods on the class. The next method returns the next number in the sequence. Doesn't actually change any state. The forward method does change the state of the sequence by moving forward to give a number of steps. It calls the next method to find out which number is next as it takes each step. Now I can print out some values in the sequence like this. Now for something interesting. We defined the forward method in a nice general way so that it doesn't actually know anything about the sequence. It just calls the next method, which encapsulates the order of the sequence. So we can make a subclass that prints out a different sequence by overriding the next method. Let's do that for square numbers. Squares is a subclass, so it may be surprising to see that it begins life as an instance of sequence. This is actually a nice way to implement inheritance in Lua. It works because classes and instances are all just tables, and instance behavior is based entirely on metatables. In a minute, I'll show a diagram that illustrates the relationship between the square and the sequence tables. Here is how we can use the square subclass. Yay, it works. Now, let's take a look at a class diagram. This focuses on the three tables SQ, squares, and sequence. We're thinking of sequence and squares as classes because they have access to a constructor and the forward and next methods. When we look up a key on SQ, Lua will use the first value it finds in the metatable chain. So, calling SQ next will call the next method associated with squares, and not the one associated with sequence. It's interesting to carefully consider a call to SQ forward because somehow the forward method has to know to call the version of next in squares, and not the version in sequence, even though forward itself is defined in the sequence table. First, Lua finds the forward key defined in sequence by looking up the metatable chain. Then, forward makes a call to self next. What is the value of self? It's set to SQ. So when forward calls self next, Lua begins the lookup starting at the bottom of the metatable chain with SQ itself. So any methods defined in squares get to override methods defined in superclasses like sequence. This is how single inheritance works in Lua. It's also possible to use multiple inheritance in Lua, which is where a class may have more than one immediate superclass. I won't cover this in detail in this video, but I'll mention that the key idea is to use a function as a metatable's index value instead of a table. I actually covered all of the Lua material that I wanted to cover in this video, but I'd like to end with something fun, which is a concrete example using a lot of the things that we've just gone over in an app that will act like a graphing calculator based in the terminal. It will receive a mathematical function as an input string, and it will use ASCII characters to draw the graph of that function. So let's make this script. I'll call it lgraph for Lua grapher, and I'll begin with a hashbang string so that I can call it directly from the shell without having to consciously use the Lua interpreter. Oops. And I'm going to start with a multi-line string here, which is a usage string, and I like to do this because programmers looking at this script can see the usage right away at the top of the file, and then it's assigned also to a global variable which I can later use to print out to the user what's going on. And right now I'm just setting up the structure. I plan to explain and program this in a top-down manner, meaning that I'm going to start with sort of the highest conceptual level thing happening here and define more and more detailed pieces as I need them. So I'm going to define a class called grapher. So at the very end here I'm going to declare an instance of that class, and I will call this graph method on it with arg1. Arg is a special built-in variable name that the interpreter populates with the strings that we get from the command line. To be nice to the user, if they have not given us an equation to graph, instead of just having a horrible failure, we'll notice that and we'll print out the usage string, and we'll exit politely. Now we're ready to define the grapher class itself. So I'm going to start off with just a table of regular values, not functions yet. I'll define my X window, my Y window, number of columns in ASCII to print out, number of rows as well. I'll just hard code them for now because it's simple to do. Here is a constructor. We'll make a local table. I have to make sure the index key is set to self, and then I'm going to return the new instance with self set as the metatable. And now we're ready to define this key function, the graph function, which receives a equation string as input. Now, I'm going to delegate a lot of my work to this setup care table method that I have not written yet. I will write it. And the idea there is that I have this self.care table, which is sort of like a two-dimensional array conceptually. And that will give me a way to very easily iterate over all the rows and columns as I'm doing here right now. And if there is no value there, if it's nil, I'll just write a space character out. If it's not nil, then I'll write whatever character is there out. Okay, so that's what that current code will do. That's the complete graph function. And really, it's not doing any really intelligent work because I've delegated it all to this setup care table function, which is going to do the real work here. Now, this line is probably going to be the most single interesting line because it's actually going to do the most non-trivial work in the whole program. And what I'm going to do is parse and compile equation as basically Lua code. So completely insecure code. Security vulnerabilities there. But let's pretend the user is a very friendly, nice person. And let me explain this ... notation because this might be confusing. When Lua compiles something using load or load string, ... is sort of like a macro that expands to be all the parameters that are given to the function f. Remember, load string returns a function. So if I were to execute this y equals f of 3 line, then this code would be executed with x set to the value 3. And then let's say EQN was set to the string x squared. Effectively, the function f would be x squared, so the value of y would be 9. And really, EQN could be any valid Lua expression, and as long as it depends on x and no other variables, then we have whatever function the user wanted to define. So that makes it easier to write a graphing calculator. A very insecure graphing calculator, but a graphing calculator nonetheless. Now, I have not yet written the function rangeMapper, but I will. And that function gives us exactly a linear mapping between two ranges, between the beginning range. In this case, I'm mapping ASCII column space into the X space mathematically. And then based on those two things, what I can do is I can basically go through all the columns that I care about, and for each column I can figure out what the mathematical y value is based on col. Then I can use that mathematical y value to convert back into ASCII space. Oops. That. And essentially what I want to do here is I want to set self-character col row to be equal to O. Now, it may be the case that col row can't be set yet because col row, this value right here could be nil. Basically, this could be the first thing I'm putting in that particular column. In fact, most of the time we would expect that to be true. Oh, I wonder if I could actually just make a shortcut. Probably I could just do that. Let's try that out. Okay, great. So now I've done everything except for these two supporting functions that I haven't defined yet, but I've used. So I've defined, or I've actually used two functions that I haven't defined yet. One is called round, which is really easy. This is just going to round to the nearest integer, which is the same as taking the floor of x plus half. Now this function, rangeMapper, is a little more interesting because it's going to return a function that I have to make on the fly. And conceptually what I'm going to do is I'm going to calculate this percentage that the input is from A1. So the input is sort of a number in the range A1 to B1. Okay, so I'm just going to turn that into a percentage, and then I'm going to return that percentage converted into the A2 to B2 range. Okay, there's a very good chance that I've made some typos along the way, so let's take a look at those typos. Let's see. So I forgot to write the word set there. Now let's try this again. 19, let's see, percent from A1. There we go, great. Only 2 typos so far. Let's make a more interesting graph here. Sweet, there's a parabola. Let's do one of my favorites. Let's do some little trig. Oh yeah, that's looking good. Let's do something even more interesting. Here's a nice trig function. I like that. Now I'd like to extend the functionality of this script by being able to optionally draw the x-axis and the y-axis. And I'm going to do this by subclassing the grapher class. I'll make a subclass called axis grapher. And to be honest, the point of making a subclass here instead of just adding functionality to the existing class is to illustrate what it's like to make a subclass. So if I were not using this in a tutorial video, I might not implement it exactly this way. Now I've set up the base class so that I really just need to override this one function, setup char table, in order to slightly modify the behavior of the base class. Now what I'm doing here is I'm making a call to the superclasses version of this method, and I have not used the colon syntax in that line because I want self to be the value of self that I receive in this method call, but if I used colon here, then grapher would be set as self inside the call. So there's sort of, in this special case, there's sort of a case where I cannot use colon syntax. I have to be very conscious of what object owns the method and which self is. Self might not be the same as where the method is. So that's kind of a special case when you call super. All right, so now what I've just done is I've set C for column to the column that represents the y equals 0 column. X equals 0, I'm sorry. And now I'm going to iterate R over all possible rows, and I will set that character to be a vertical bar. We can make that a one-liner, why not? And now let's draw the x-axis. And so again, I'm going to use range mapper to map my y equals 0 value into the row value, like that. And now I can iterate over all columns, and this time I'll use a hyphen as the character. And that's everything I need to do there. Now, if I'm being careful about parsing the command line arguments, then basically the way I'm going to check if they want to use access is look for -a as a flag. And if they have that flag, then I expect there to be another argument, arg2. And so I'm going to act differently depending on whether or not the first argument is a -a. If it is a -a, then my global variable g will be an axis grapher instance. And for convenience here, I'll copy over the math equation to graph into arg1. So that way, from this point on, arg1 is always the equation to graph. If there was no -a, we'll continue to use the original grapher class as the instance. Now, if I've done everything correctly, great. So now I can even edit this instance here. There we go. There's our axis. All right, that's actually everything I wanted to cover in this video. I appreciate any likes. Please subscribe. If there are any topics that you'd like to request for future videos, please request them in the comments. I do plan to continue posting tutorials on programming topics in general. Here are links to the Twitter accounts that I have. And thanks again for watching.